Okay. In the last video then we talked about how we were going to quickly look at how we go about designing a structure, and the structure that we started to look at was a park bench, and that bench consists of a back, a seat and some legs, breaking it down into the structural elements. So this structure has to perform a function, and that function is to support the weight of a person or people sat at some point on the seat of the bench. And we will tend to refer to, in our analysis section of these videos, a point load as being P, or a weight. Sometimes we'll call that a W for weight. So those are mathematical variables which we will use. And that weight, that load acting down, exerts a force on the elements of the structure. So for example, we might pick a particular, if I draw it a bit neater, a particular plank that makes up part of this bench, and that load will then have to distribute. So it comes in on at this point here, and it has to distribute towards where this plank is supported, which would be typically at the ends. And we may have another structural element which is a stiff down stand, and we might have one where each of the legs are. So we've got a beam that acts here, which picks up all these planks, and one this end. So we'll have a plank that's supported essentially between these two beams, and those beams carry the load then down into the legs of the park bench. So those loads come down each of these four legs in this case to the ground where it's supported. And in order for this structure to be in what we call equilibrium, static equilibrium, which is something we will talk about in the analysis section of these. Static just means that it's stationary, it's not moving, and equilibrium just describes the fact that this thing has to be equally balanced, such that the forces exerted on it, the external forces, are balanced through internal forces within the structure, such that the structure that we're looking at, either globally or locally, doesn't move, it remains static. So in order to do that, we've got this load acting downwards. So if we say positive is in the upwards direction for the purposes of our sign convention, we've got a negative force acting downwards, and that needs to be balanced by some vertical forces acting in the equal and opposite direction. So equal value or equal magnitude of force acting in the opposite direction. And that will be made up of four reactions. So we call this an action. This weight of a person we call an action, and that's acting in this case in the downwards direction, or the negative up direction if we say that up is positive. So we need to have a reaction to that force, to that load, and these reactions come from the ground at each of these four locations, and they will, depending on if this was bang in the middle in both directions, each of these reactions would be equal. but we'll say that in the general case, this load could be anywhere on this structure. So we will have 4 reactions, which we'll call R1 through to R4. Okay, and then for static equilibrium, we need to satisfy the fact that for this bench in the vertical sense to stay stationary, that's to say if it's not to sink into the ground, then the ground has to provide equal and opposite forces which added up together sum the force in the downwards direction. So we use the symbol, the Greek symbol capital sigma, to say a sum. So the sum of all our actions, and we'll call them forces. So we'll just give them the title F in the vertical direction. So we'll call those FV. And we're just choosing this convention of calling these, referring these variables. So the sum of all the forces in the vertical direction have got to add up to 0. Okay, so basically what's that saying? That in this case our P plus, all these are forces that have a component in the vertical direction. In fact, all those forces are only acting in the vertical direction. There are 3 directions: horizontal, vertical. So we could look at forces that act horizontally and act out of the page, as it were, if this is our system of coordinates. But we're just looking at in the vertical direction for the moment. So P plus R1 plus R2 plus R3 plus R4. For this thing to be in equilibrium, in static equilibrium, all those have got to added together equal to 0. So if our force P was, let's say, had a value, some value of 4, and we won't give it units. It's got some units of force, let's just let's give it a set of units. Let's stick with 4 kilonewtons for now. Which we'll come on to talk about whether that's a sensible load to put on this type of structure. But just to make things mathematically easy, if that force is in the bang center of this seat, so equally distant to each of these legs of the bench, then each of these reactions would come out at 1 each, because that force would equally distribute. And then for static equilibrium, each of those reactions would act in the upwards direction, so in the opposite sense to this load, and added together would give that reaction, or would give the total sum equal to 0. So we would have 4 in the negative sense, in the downward sense, so minus 4 plus 1 plus 1 plus 1 plus 1 is equal to 0. So we've got minus 4 plus 4 lots of 1 equals 0. So we have satisfied our requirements for static equilibrium in this case. And what that means is that this structure isn't going to move in the downwards direction or the upwards direction. If it wasn't possible, if the ground was too soft, for example, and we couldn't provide the full reaction underneath each of these legs, then this would be out of balance and that would sink. And as it sank, we'll talk about elastic deformation of solids, and that would produce more force. So it would sink until the point at which the force balanced back, and we got static equilibrium where the sum of all our forces came to 0. And then we would have static equilibrium, and the structure would be a static structure. Most civil engineering structures that we're going to look at are not moving, certainly in this set of videos. The structures that we're going to be looking at have no movement or rotations involved. In the next video we'll look at the 6 degrees of freedom in translation and rotation for a 3-dimensional body, and we'll look at the system of equations of static equilibrium for a structure in those 6 degrees of freedom. Okay, thank you.